Welcome to our webinar today on the value of Valor NPI in a design flow. The new product introduction process spans both the design and manufacture of printed circuit boards and requires a clear and complete communication between the two. Mentor's Valor NPI application software helps you accelerate your new product introductions by recognizing the manufacturing impact of PCB design, optimizing the design for volume production, and communicating complete PCB design data to manufacturing. There are multiple steps in the new product introduction business process. The first questions are, does it work? Can it be manufactured? And how? During ramp to volume, it's what can be done to improve yield, alternate parts, alternate build locations. For volume through end of life, it's lowering the cost of production and improving product reliability. Using prototyping and production to find DFM issues is time-consuming and expensive. A rule of thumb for design is that it costs 10 times more to fix a problem with each step, and the most expensive failures are the ones that you find in the field. So DFM shift left reduces the time and expense of fixing DFM issues and optimizes NPI success. Or a manual review of the design is done at the end of the design cycle. This is still too late and results in either a delay in the release or a decision to defer changes to the next revision. DFM is part of your review and release process today, but it often is done differently with different tools or even manually. The results are an inefficient and error-prone process to create and validate the manufacturing package. An Aberdeen study found that companies not using Valor DFM average 2.8 revision spins per design. Valor NPI complements the design rule checking you are already doing during the design cycle, adding checks that can impact the manufacturability of the PCB. Many of your suppliers are already using Valor to check your design when they receive it. You can check the designs earlier using rules aligned with your supplier's capabilities and aligned with their manufacturing processes. Different manufacturing processes may require more specific checks than those found in traditional DRC. For example, DRC may check for a minimum annular ring, but DFM will check the annular ring based on the manufacturing process, laser drilled, mechanically drilled, or back drill configurations, for example. DRC has a drill to copper spacing rule, but DFM will analyze the drill to copper spacing based on the manufacturing process, plated through hole versus non-plated through hole, for example. The MRA is our main tool to facilitate the review of any number of analysis results, and it does so by grouping them into assessment areas. Each area relates to a specific fabrication or manufacturing problem or process. A summary pane provides an overview of results of all assessment areas and categories. The MRA can be used to sort and review analysis results, isolate issues that will most affect quality and yield, define groups and run analysis actions, and report issues of interest. The Valor Parts Library provides standardized information about the components that will be mounted on the board based on the manufacturer and manufacturer part number in the BOM or AVL. A standard boundary definition and height property allow a wide variety of checks beyond standard DRC rules. The pin information allows a virtual build of the board to be performed, identifying pin-to-pad issues that can affect the quality of solder joints. Solder validation requires comparing the CAD footprint in the design to the pin contact area of the pin from the Valor Parts Library, allowing the checking that the solder DFM rules are met and validating measurements such as toe, heel, or side solder requirements for rectangular pads and periphery requirements for ball pins. The MRA Revolution was first introduced in the Valor NPI 10.0 release and has been expanded into assembly analysis with the current 11 release. This has allowed Valor to pioneer the concept of automated manufacturing process-driven DFM. The MRA Revolution is a new approach to DFM rule creation. It greatly simplifies the process, making accurate DFM results much easier to achieve. It makes use of PCB design technology and process constants to automatically determine the DFM analysis to run, as well as the DFM rule values to utilize. It provides a more streamlined DFM process and eliminates the need for legacy ERFs and checklists, and makes concurrent DFM needed for the left shift methodology we discussed more practical. MRA Revolution can be set up to understand the stage of the design and perform only the analysis needed at the stage of the process. Manufacturing process-driven DFM is as easy as 1, 2, 3. To properly assign the appropriate constraint rules to the design, we have the ability to set up various design factors to help make these assignments based on attributes within the design. In this example, we have added factors such as drill size, copper weight, layer count, typical trace-to-trace spacing, as well as typical trace width. The next step is to define classification sets, setting up this product model-centered approach to the DFM that we call MRA Revolution. The system will interrogate the design for these factors, and for any classification that fully passes, the system will assign the constraint values. There can be many different classifications, such as technology types, design stages, or possibly vendors. Then the third step is to update your constraints for both the classifications and the factors in the constraint areas so you can easily fine-tune exactly how you want the setup to your rules to analyze your design. For example, we can select factors such as copper weight of 1/2 ounce, 1 ounce, or 2 ounce, along with layer side for inner and outer layers. Now we can select each of the constraint categories and set up constraint values for these factors. Here is an example of manufacturing process-driven DFM. Based on the factors in the design, Valor can determine if the design contains any micro-vias based on the standard IPC definition. If the aspect ratio is less than or equal to 1.0 and the depth is less than or equal to 9.84 mils, then micro-via analysis is automatically performed. If there are micro-vias and at least one layer designated as a build-up layer, then the HDI DFM analysis will be executed automatically. Valor NPI is the only DFM software that is manufacturing process-driven, using the knowledge of which manufacturer processes apply to automatically determine the correct checks to run and DFM rules to use. When the design is read into Valor, the design factors drive the design classification, which then drives the manufacturing constraints. All this is based on the software knowing the manufacturing processes applicable based on the design. Running design for manufacturing checks during the design process supports the shift-left methodology we discussed earlier. Finding DFM problems earlier in PCB design saves time, as fixes can be more difficult at a later stage. Running incremental DFM analysis means that the issues that are identified directly to the engineer responsible for that stage of the design and release process. Another interesting effect is that it helps PCB designers to become more aware of design choices that affect the manufacturability of a PCB. Running Valor NPI even before placement can identify library issues, such as incorrect pin-to-pad size or pad alignment. It can also identify graphic silkscreen or improperly defined gang masks for fine-pitch devices. Valor checks after placement can identify problems such as component clearance violations based on the standard component definition from the Valor parts library, components too close to a conveyed edge, or even tall components too close to adjacent components, making it difficult to access the short component for repair. As someone once pointed out to me, changing component placement after routing can be difficult. It's like the components are mounted in cement. Running the DFM checks during routing can identify common fabrication issues, such as slivers that can cause repeat defects due to photoresist flaking, starved thermals, and circuits too close to the mass clearance around a pad that can result in solder bridging during the assembly process. Flex and rigid flex circuits have their own manufacturing requirements. Conductors need to be perpendicular across the entire bend area. Plated holes need to be a sufficient distance from a stiffener. Rigid area copper too close to interface areas can cause copper to crack. and silver mask must remain clear of exposed copper to avoid EMI issues. Validation of the manufacturing BOM assures that there are no ref des or quantity mismatches. The pin area component data from the Valor parts library allows the virtual mounting of the components on the board, identifying solder issues that can lead to weak solder joints, such as insufficient heel or toe distance. Even the ratio of heel to toe can affect the quality of a solder joint. The component outline data can identify other issues. For example, shown here is a case where the actual component body, shown in red, covers a mounting hole that the CAD package outline, shown in purple, didn't detect. At this stage, alternate part lists in the BOM can be analyzed. In this example, components A, B, and C are listed as alternates in the bill of materials. Components may have the same electrical properties but different body dimensions and pin contact areas. To confirm that no matter which qualified parts are actually sourced, there will be no manufacturing issues. Each of the qualified parts are compared to the footprint in the design. Valor simulates the mounting of component A on the board. In this case, a toe violation is identified. Component B is validated. For component C, there is a pin to pad side violation. The final review brings all elements together. If the DFM checks are not run until this stage, you can be spending time fixing issues that would have been identified earlier, delaying the release of the board. A few additional examples are shown here, such as different trace widths connecting pads can cause a component to tombstone during reflow. Traces under a zero offset device may cause a component to rock, resulting in a poor solder joint. Adjacent layer copper may make it difficult for SMT equipment to identify local fiducials, or too many test points within an area can stress the PCB, potentially affecting the solder joints in the area. If the checks are being performed during the design cycle and manufacturing issues addressed as they are found, then when the design is released to manufacturing, there may be no more issues and the board can then be built. I hope we've been able to show how using Valor NPI for an efficient and effective design reel process can result in lower PCB costs, improved PCB reliability, and a streamlined release process. In that Aberdeen group survey we quoted earlier, they found that companies using Valor DFM averaged 1.2 revision spins per design, a 50% reduction, resulting in a significant savings in material cost. Let's move on to a demonstration of a typical Valor NPI analysis. The Manufacturing Risk Assessment Tool, or MRA, is the main tool to facilitate the review of any number of analysis results, and it does so by grouping the analysis results into assessment areas. Each area relates to a specific fabrication or manufacturing problem or process. The summary pane provides an overview of the results of all assessment areas and categories. The MRA can be used to sort and review analysis results, isolate issues that will most impact quality and yield, define groups and run analysis actions, minimize design errors, and report issues of interest. From within your EDA tool, simply export your design directly to Valor NPI or through the process of exporting ODB++. We can then open your design from within Valor NPI, where we can quickly see the intelligent information, such as proper layer stackup, along with your drills that interconnect your layers. If we take a deeper dive into the layer stackup, you can see additional intelligence that automatically came from your EDA tool, such as copper weight for each layer, build-up layers versus core layers, material thickness, and layer subtypes, to name just a few. Valor NPI has the ability to easily import your bill of materials along with alternate part information to make the design even more intelligent. Once the BOM is imported, we can run a match with the Valor parts library to automatically assign the VPL parts, which allows you to use the more comprehensive pin contact information from the VPL solder validation, as well as other assembly DFM analysis. The MRA is also the gateway to the Analysis Definition Manager, also known as the ADM, which is used by the DFM expert to define classification sets for the newer product model-centered approach to DFM that we call the MRA Revolution. From within this ADM, we make use of the intelligent information that comes over to tune the analysis based on critical attributes of the design. To properly assign the appropriate constraint rules to this design, we have the ability to use various design factors. In this example, I've added factors such as layer count, typical trace-to-trace spacing, as well as typical width for both inner and outer layers. As you can see, we select the test button, and the system interrogates the design and lets me know which of the factors pass. For the first classification that fully passes, such as complex 4-4 mil in this example, the system will assign the constraint values to the design based on this complex classification. Once I jump over to the constraints, you can see that I have made use of additional factors such as copper thickness and layer side. I can also test any particular constraint from within the ADM to make sure I am receiving my desired results during my one-time ADM constraint setup. Once you have completed the setup of the analysis definitions, running the analysis from the MRA is accomplished by a single action from within the analysis menu, Run MRA Revolution. From here, I simply select your preferred classification set. This single action triggers the Valor NPI to analyze your design and automatically select the most appropriate constraints based on the factors of the design. The analysis will be categorized within the MRA for your review in one fell swoop. Back in the MRA, we drop into the etch type results first, where we will select, for this example, the fabrication concern slivers. Once we select the issue, you can see that it zooms to the location in the design. We can easily synchronize the design with the EDA tool, making it easy for the designer to make the update directly within the source data. Additionally, if we need to tweak the ADM values for this check, I can simply select the Open ADM icon, and it will take me directly to the constraint world where I can quickly make a change. As you can see, this issue was on layer 4, which is an inner layer, and the yellow value of 4 mils, but the measured value of 1.277 mils, if I have permission to choose to tweak the value within the ADM, I simply select my complex 4x4 mil rule for inner layers and make my change. Now for our second example, we'll jump down to the solder tab to look at solder validation issues. As you can see, the system flagged a number of pin to pad issues. As we select one, we can see the actual pin of the device that came from the BPL match has a heel distance violation. There's inadequate space at the heel of this part to achieve a proper solder joint. We're looking for 13.78 mils based on the IPC level B rules, while we only have 4.25 mils. You can see here the red box is the pin and the part, while the darker blue is the copper pad. For our last result review example, we'll select a component placement issue where we have a discrete 1206 too close to an SOIC. As you can see, we are looking for a 15 mil clearance and only have 10 mils. Once you have completed your analysis and optimized your design, you have the option to generate your ODB++ output, which supports fabrication and assembly while protecting your intellectual property.